This episode is brought to you by Squarespace, because why not? They already sponsor everybody else on the internet. How many subscribers you got? 10? Fine, good enough. There you go. No, I'm not actually sponsored by Squarespace. If the YouTube guys are watching, don't take my little ad away, wherever it may be. Or it might have been a video. I don't know. I need the nickel. So I do, my website is Squarespace. This guy. But no sponsorship. So last week, I made the mistake of telling what I was going to do this week because I actually changed my mind. I should stop doing that. I was going to talk about some more thermochem stuff, but I decided to go ahead and get to quantum numbers. But the general two guys, we're going to still talk about buffer calculations. Right. And let's just get right to it. So, starting with the Gen 1 guys. Yeah, my thing went away. There we are. Phrasing. Let's see. And both halves are going to be on PowerPoints because I actually had time to put together some slides. Some of the stuff I'm actually going to keep on my real class because I don't always just pull my lecture slides. Actually, most of the time I actually make up new stuff for the people who actually have already seen it in class. But in here, there we go. All right. So with quantum numbers, one way to think about quantum numbers is that they give an electron its address. You're already familiar with an address. It's much like this U.S. address. If you guys a street, city, state, and a zip code that's pretty much a city in the state, but we still do include the city state anyway. I guess so the postman did get confused until they're replaced by robots, which I guess we just use a zip. And I, for one, welcome our new postal overlords. Anyway, but if you kind of read it backwards in the way you normally do, bottom top, if you look at it that way, then as you go from the bottom to the top, every little bit of information gets you a little bit closer to where you might live, given your address. Say you live in this state, in the state you live in this city, you're on this street, and on the street you're in this house number, and possibly an apartment in that house. But every little bit of every little thing gets you closer and closer to where you might be in the United States or wherever you may be on Earth. Quantum numbers kind of work that way, at least the main three quantum numbers, which we're going to talk about. As you go, if you look at them in sequence, each one gets you a little bit closer to where that electron might reside. Before we do that, though, just to remind you of how the model before that worked, which is attributed to a guy named Bohr. Niels Bohr is known for two things: the stuff that you learn in Gen 1, and also for apparently having a kind of a feud with Einstein. History likes to call it a friendly feud. Maybe it was. Maybe Bohr hated his guts. We don't know. A lot of people know Einstein's quote, "God doesn't play dice with the universe." People don't give Bohr enough credit for his comeback telling Einstein, "Don't tell God what to do with your dice." But Bohr's model of the atom is basically the same kind of the cartoony model you guys are familiar with. He had these things called energy levels, which are often labeled with the letter N. And we don't usually look at it this way with all the little circles going diagonally and such and whatever. In most chem books, we look at them flat. So you have your nucleus in the middle. Your first energy level would be closest to the nucleus. Your second energy level would be further out. And your third one would be a little further out, and so on. It's basically kind of like the planetary model of our solar system. And if or when you learn about Bohr's model in class, you find out that Bohr's model's pretty good. It's good enough for him to get a Nobel Prize. But it wasn't complete, mainly because it only worked with one element, hydrogen. But the fact that it worked with one element meant that he was onto something. But eventually, a lot of people, so names you may have heard like Schrodinger or de Broglie, come up with this quantum model, as we call it. And there's a lot of math in the quantum model because it's basically a math-centric model. And you guys can look up these different quantum numbers on Wikipedia, and you will see lots of math that probably you don't want to deal with as a freshman chem student. Especially about this time, because this is about the time of the semester, if you use the traditional format, where we stop doing any kind of math at all. So these quantum numbers are used in an equation somehow. We don't care how. We just kind of look at them sort of qualitatively. So there are some things qualitatively that these numbers can tell us without having to do a bunch of freaking math. Right. So the principal quantum number is basically the same as Bohr's N. Although we don't usually call them levels at this point, we use the term shells. My guess has always been that shells make you think more three-dimensional, which is what this theory really is. With Bohr's model, it seems more flat. But again, it's the same ends. So it's just any positive non-zero whole number can be a value of n. So n equal 1 represents the first level or shell, like we saw in the previous slide. Second shell is n equal 2, and so on. The next quantum number, sometimes called the angular momentum quantum number. Sometimes it's called a different quantum number. It refers to the sublevels or subshells that can be in a given shell. So the rule is that for whatever shell you're at, whatever the value of n is, L can be 0, 1, all the way up to n minus 1. And again, these numbers are used somehow in some equation. At this point, we don't care. What's important to us is how many of these values of n we end up getting, or sorry, these values of L we get for this value of n. Because the number of values of L you get equals the number of subshells that are in that shell. So for example, if you're talking about the first shell, the only possible value of L in that case is 0, because 1 minus 1 is 0. Right. So again, numbers mean math something, but for us, all it means is that that first shell only has one subshell, which is kind of redundant if you think about it too much, but it works better for the later shells. Like shell number 2 has 2 possible values of L, 0 or 1. So again, we get 2 possible values of L. What that means to us is that there are 2 subshells in the second shell. 2 subshell. Forgot to pluralize. Oh, whatever. Me not talk so good now. You go on to shell 3. You have 3 possible values of L, 0, 1, or 2. And notice the pattern here. The nth shell has n subshells. There are lots of patterns with these quantum numbers that can be kind of handy. So the first shell has 1, the second shell has 2 subshells, and so on. The third shell means the 3 values of L means there are 3 subshells that are in the third shell. And it kind of goes on from there. Now, dealing with all these numbers can make your head hurt unless you really, really like numbers. Unless you're like Neo, just looking at those little green numbers that are falling down in the matrix. But for most normal folks, looking at all numbers can be kind of a pain. So what we've done is we've assigned values of letters for these different possible values of L. So for the first 4 values of L, 0, 1, 2, and 3, we've assigned the letters S, P, D, and F. So S means L equals 0, P means L equal 1, and so on. And these letters meant something at one point, but they've kind of lost their meaning. Even some chem books don't even bother telling you, or they'll just tell you in passing or maybe as a footnote. It doesn't really matter for us. In fact, it doesn't matter to a lot of people, it seems, because people decided that after L equal 3, they said, screw it, we'll just go alphabetical. So, 3 is F, so they just said, okay, G will be 4, H will be 5, and so on. And people will ask what happens when you get to whatever L is O. Are you going to skip P, or are you going to do it again? We probably won't have to worry about that for a long time. You'll see that as you get more into electron configurations, actually putting electrons into these different shells and subshells. All right. So for example, when if you're in the third shell, n equal 3, and you're at whatever subshell is L equal 2, you could have said just what I said, the L equal 2 subshell and the third shell, or you could say the 3D subshell. And if you're looking at the principal quantum number 4 and the angular momentum quantum number 2, instead of saying what I just said, we'll just say the 4D subshell. So again, nice little trend here that you see is, notice that the number tells you the N or shell you're talking about. The letter tells you the L. Tells you what L you're talking about. So that's handy, number N, letter L. So again, the number represents the shell, the letter represents the subshell. So it's just a much more convenient way to talk about these things instead of just working with all numbers. So finally, the third quantum number that we'll talk about, the third one that's related to the other two, is called the magnetic quantum number, which is M subscript L, or M sub L. And it refers to the sub-sub levels or the sub-sub shells, or we usually just call them orbitals. It's kind of a throwback term to Bohr's theory. Also, sub-sub shell doesn't really sound good coming out of the mouth of a scientist. So it tells you how many of these sub-sub levels are present in the sub-levels or orbitals in a subshell. So whichever subshell we're talking about, the values of M sub L are going to go from negative L up to plus L, including 0. So again, the number of allowed values is what we're looking at. However many M sub L's are allowed for that particular value of L, that tells us how many orbitals are in that particular subshell. So for example, let's say you're looking at the D subshell, where, and again, D is the letter we assign for L equal 2. The number of M sub L values are negative 2, negative 1, 0, plus 1, and plus 2. So you have 5 allowed values of M sub L. What that means to us is that there are 5 orbitals in a D subshell. And again, another little trend you see is that the number of orbitals is equal to 2L plus 1. The 2L basically comes from the plus or minus numbers. The plus 1 is the 0. So S gets to be handy if you're going to higher numbers, like, say L equals 8. You say, oh yeah, 2 times 8 plus 1 is 17. So 17 orbitals in whatever is L equal 8 slitter. So looking at the first 4 shells, again, the first shell only has one subshell because it only has one allowed value of L, and we call that 1s. There's only one allowed value of M sub L when L equals 0, because you can't have plus or minus 0. So what that tells us is that there's one 1s orbital in that first shell. So that's all the first shell is just a 1s orbital. You move on to shell 2, you have 2 subshells, 2s and 2p, because L can be 0 or 1. And in the S subshell, you only have one s orbital, because there's only one possible value of M sub L for that particular L. And there are three possible values of M sub L when you're talking about the P subshell, L equal 1, -1, 0, and +1. So in the second shell, you have 1 2s orbital and 3 2p orbitals. Shell 3, you've got a 3s, 3p, 3d. You got 0, 1, and 2, SPD. And again, notice that no matter what shell you're in, you only have one s orbital in that s subshell. The s's always come single. P's always come in sets of 3 because P always stands for L equal 1, and you're going to have 3 allowed values of M sub L for L equal 1, -1, 0, and +1. And like we saw before, for a D subshell, you got 5 d orbitals. And finally, in the fourth shell, you have 4 subshells, S, P, D, and F, which means you have 1 4s orbital, 3 4p orbitals, 5 4d orbitals, and 7 4f orbitals. And again, another trend you see, you got 1, 3, 5, 7, so we're dealing with odd numbers. So if we went on to shell 5, 5 should have 5 subshells, 1s, 3 ps, 5 ds, 7 fs, and 9 gs, if you actually worked it all out. But I've run out of slide space. So kind of going back to the street address analogy, and you can think of the principal quantum number, the n, as being that bottom part of a mailing address. It gives you an idea of where an electron is going to be. L hones it in a little more specifically to what street in that city you're talking about. And the M sub L tells you where on that street, which house on that street, or what orbital in that subshell you can find a given electron. So that's a little bit of how quantum numbers work. There's a fourth quantum number, M sub S, but we'll save that for another possible discussion later on. All right, so moving on to General 2. All right, so for the General 2 guys, again, I did PowerPoints because I actually had time. A lot of times I don't have time. Actually, I just scribble some crap down and then I just use my tablet thingy to do it in Word. But today I thought, you know what, we'll see how it looks if it's all PowerPoint and nice and neat. Or maybe it's going to look too nice and neat and I want to go back doing writing because I don't want it to look too nice, which is good because I don't have any money to put in production. Again, I'm in my office, in my house, so no studio. I can't even figure out how to do a picture-in-a-picture thing, although you really don't need to see me while I'm doing this, do you? Although, fun fact, I do still point and do a lot of motions when I'm talking with the PowerPoints or the tablet running, but you can't see it. But you can just imagine me doing it now. But anywho, General 2, all right, so talk a little bit about buffers. And remember how a buffer, or what a pH buffer is. pH buffer is basically a solution that keeps the pH from changing a lot. Can't hold it rock steady, but it'll keep from changing a lot. And you need two things for this to work. You need a weak acid and you need a salt of its conjugate base. So the way the weak acid works is that any base that you add to that buffer solution, it's going to get neutralized by the weak acid. And just a regular classic neutralization reaction. Acid and base give you water and a salt. Although I'm leaving out the cation. Usually the cation is usually sodium. Sodium, whatever the anion is. The conjugate base is going to neutralize any added acid that you add to the solution. And this one's more of a, showing it this way, is more of a Bronsted-Lowry type of reaction, proton donor, proton acceptor. But still, it's a neutralization. It reacts with the acid to give you, whatever its conjugate is, and your weak acid. Because again, these are conjugate pairs. Right. So usually for buffer calculations, you use the weak acids equilibrium equation. You can actually use a base equation and it works fine, the base and it's Kb, but most people use the acid Ka combo probably because the Kas are a little easy to look up. Or usually most books have a bigger table of Kas than they do Kbs. So let's say this imaginary acid, whatever it is, has a Ka of 2.5 times 10 to the negative 6. To do these calculations, we're going to use the Henderson-Hasselbalch equation instead of an ice table. Ice tables work, but by this point, pH, the Henderson-Hasselbalch equation is usually a little quicker and easier to use. And let's face it, by this point in the course, you're probably sick of doing ice tables after, what, two and a half chapters, depending on what you talked about. So you just need the pKa, which, again, P anything is, oops, the negative log of that thing. So the pKa is the negative log of the Ka. So for this, whatever the acid is, its pKa would be 5.6. Now you just add the log of the base acid ratio, your conjugate base acid ratio. All right, so if you start with 2 molar of your weak acid and 1.5 molar of this conjugate base, that initial pH of that buffer solution, plugging these numbers into your Henderson-Hasselbalch equation, is going to be about 5.48. So let's say you take this buffer solution and you add 0.25 moles of sodium hydroxide to a liter of this buffer. And the liter, using a liter is a little trick to keep things simple. That way the molarity in mole is the same number. Right. We're also assuming the volume of the base isn't going to be significant. Again, it's just, we're trying to keep it simple for these early problems. So again, we're adding a base to this buffer. So your weak acid is going to neutralize this base. Again, in a classic acid plus base, give you water plus salt type of reaction. Or if you show it as a net ionic, it would look something like this. So there was 0.25 moles of hydroxide present. It's going to take that much weak acid to neutralize it, because it's a 1-to-1 relationship. And in fact, everything's 1-to-1. So you're going to get that same amount of conjugate base produced from this neutralization process. So if you go back to the original equation for this buffer system, we started off with 2 moles of weak acid, 1.5 moles of conjugate base per liter. And after this neutralization process happens, we're going to lose 0.25 moles of our weak acid, gain 0.25 moles of our conjugate base, which means after everything's done, we're going to, with 1.75 moles of weak acid and 1.75 moles of conjugate base. So you take those new concentrations, because again, we're doing the mole molarity cheat here, plug those in the Henderson-Hasselbalch equation, and you get 5.6, because log of 1 is 0. So originally it was 5.48. So it went up a little bit, around 0.1 pH units. You compare that to adding that same amount of base to a liter of just water. Again, there's nothing to react with the base, so it's just going to dissociate to give you sodium and hydroxide. So you end up with essentially a 0.25 molar hydroxide solution. That'll give you a pOH of 0.6. Subtract that from 14 to give you a pH of 13.4. So if you had just say it's pure water with a pH of 7, that's over a 5-point increase on the pH scale compared to a little over 0.1 for a buffer solution. So again, buffer solutions don't keep the pH completely steady. It does change, but only a little, especially when you compare it to non-buffer solutions like pure water. So let's try another example. This time we'll take that same buffer from the first slide. Well, technically the second or third. And no, second. This time we'll add about 1/3 of a mole of hydrochloric acid to this buffer. And again, we're going to do the mole equal molar trick here. So this time we're adding an acid. It's going to be neutralized by the conjugate base, giving us chloride and whatever the weak acid is. So again, we're neutralizing 0.33 moles of this acid. It's going to take an equal amount of conjugate base, or our conjugate base, to neutralize it, because again, everything's 1 to 1 to 1 to 1, which means we're going to produce 1/3 of a mole of our weak acid from this neutralization process. So again, looking back at our original buffer system, we started off with 0.2 moles of weak acid, 1.5 moles of weak base. After the neutralization has occurred, we gained about 1/3 of a mole of HA, lost about 1/3 of a mole of our conjugate base, which means in the end we have 2.33 moles of weak acid, 1.17 moles of conjugate base. Take those concentrations, plug them into our Henderson-Hasselbalch equation, and that gives us 5.3. So again, the pH, adding that acid does cause the pH to drop a little bit, but only a little bit, especially if you compare it to a case where you take that same amount of acid and you add it to, just a liter of water. And so that's just going to give you essentially a 0.33 molar hydronium solution. You plug that into your pH equation, you get a pH of 0.48. So again, if you imagine a pure sample of water, or a solution that started out as pure water with a pH of 7, you go from 7 to about 0.5. Again, it's over a 6 pH point drop. So unbuffered systems, the pH is going to drop a lot more than a buffered system. So again, it does change, but only a little. So buffer solutions can be pretty handy in some cases. For example, in a laboratory setting, maybe reaction can only work at a certain pH, which is something we don't talk a lot about in general 1 or 2. You'll learn it a lot more in organic if you have to take that next year. But some reactions, they only work at a certain temperature or under certain pressures, and sometimes under certain pH conditions, or they work the best under certain pH. So yeah, you want a buffer solution that's not going to, just pH isn't going to change a lot, so that reaction works as well as it can. Or there are some cases where a buffer solution is what's keeping you happy and healthy, because this is something your book may talk about, or if not, you can just look up blood buffers on the line. And basically, there's a lot of, the pH of your blood is usually around 7.4 is what most books will tell you. But there's things that your body will do in a given day, like exercise or the foods you eat, that could cause that pH to really shoot up or really shoot down, like we saw a minute ago with those water examples. And all the stuff going on in your bloodstream and on your cells, they don't really want that. They don't want things suddenly getting really, really basic, or whoops, drop my water, or really, really acidic. Didn't drop this in a tube. Yeah, there's a bunch of different buffers in your blood to keep that pH from changing a lot, which keeps you alive. So there you go. There's your buffer talk for today. Next week, we'll talk about something else. If you have any requests, just let me know in the comments, or you can send me an email, rmarkmatthews@gmail.com. Or if you're actually one of my students, send it to my work address, because I'm trying to keep you guys from sending me stuff to my Gmail address for reasons. I don't want to look at too many email boxes just to talk to you guys. So anyway, that's it for today, or this week. whatever. And bye.